Sorry about that, the camera died, so I had to move it so I could charge it. We were using the quadratic formula, we got it all the way to here. I noticed I could factor out a 2 and simplify with the bottom, so that would be -1 plus or minus 2i. So, here's another example where I had two roots, and it gave me both were imaginary, or complex. And if you're wondering how does that work, well think, this is a quadratic. There's no real roots, which means it's just shifted above the x-axis, or if it was negative, it could be shifted below, but this one will be above. Alright, so now we've seen two examples where we're getting complex roots. We saw our warm-up example, and we saw this last one where we got roots that had imaginary numbers in them. So here's the fundamental theorem of algebra. A polynomial function of degree n has n complex roots, real and non-real. Some of these zeros may be repeated. So a complex number is going to basically be any type of number we want, okay? Any number out there is considered a complex number. We can break that down into real and then non-real, which I would call imaginary. And then we're going to break that down a little bit more in this next one, okay? So our complex numbers are real or imaginary. Well, that's our roots. They can be real or imaginary too. If they're real, they show up as x-intercepts. If they're imaginary, then they don't show up at all because they're imaginary. Now we could break this down even further. If they're real, they can either be rational or they could be irrational. One of the first tools we used today was the rational roots theorem. That only tells you roots if they're rational, but roots could be irrational, they could be imaginary, and as it pointed out here, the roots or zeros could be repeated. We call that multiplicity. So we're going to try to find those roots, whether they're real, imaginary, irrational, rational, whatever. We just want to find them all. Okay, complex numbers. So let's talk more about complex numbers. A complex number has a real part and an imaginary part. This part here, A, this represents the real part. The BI, that represents the imaginary part because I is a square root of -1, which is imaginary. It's not a real number. When we put those together, it gives us a complex number. So for example, if I looked at the number 6 minus 3i, the 6 is the real part, the -3i is the imaginary part, and when we put it together, we get 6 minus 3i. So that's an introduction to complex numbers. When we do arithmetic with it, it's pretty simple. Just treat the I as a variable. So if I'm looking at 2 minus 3i plus 4 plus I, we're just going to combine like terms. 2 plus 4 is 6. That would be the real part. -3i plus I is -2i. That would be the imaginary part, and together they make a complex number. That's how you add. Now, what about subtracting? Well, same as what we would do with polynomials, we all want to distribute the negative here. So I get -3i minus 2 plus 4i, and then we'll combine like terms. -2 is the real part. 3i plus 4i is just plus I. That's the imaginary part, and then together you have our complex number. Alright, so now let's go to multiplying. So we've done adding, subtracting, and multiplying, and you're going to see it's very similar to what we've seen before. I'm just going to distribute, and 3 times 4 is 12, 3 times 2i is 6i, -i times 4 is -4i, and then -i times 2i is -2i squared. There are like terms right here, so I can do 6i minus 4i is 2i, so I get 12 plus 2i, then I get minus 2i squared. Now, this is where it's a little bit different. We've said earlier that I is a square root of -1. So then what is I squared? Well, if I square, see an I squared, I'm going to replace it with negative 1. And negative 2 times negative 1 is positive 2, so I'm going to add that 2 with the 12 to get 14 plus 2i. So that's how you do complex arithmetic. It's not too complex, except if you get I squared, it's negative 1. All right. Now, just as far as some vocabulary here, we use the words roots and zeros and solutions, and they're all basically meaning similar things. They're equivalent is what this says here. The only difference is that if you have a complex or an imaginary root, it won't be an x-intercept, whereas a real root will be an x-intercept. So when we use words like zero and root and solution, they mean basically the same thing. Another thing is that if you have a root and the quantity x minus k, if k is a root, then x minus k would be considered a factor. It would divide evenly into your polynomial. Okay, we're going to do a couple examples of multiplying when we have complex numbers here. So let's say this is our polynomial. If I read the instructions, it says write the polynomial function in standard form. Currently, it's in intercept form. That's really good for figuring out the intercepts or the zeros. It wants us to identify the zeros and the x-intercepts of the graph. Sometimes people might say, is there a difference between zeros and x-intercepts? And that's kind of the point of what we're about to see here. So if I'm looking at this polynomial here in part A, I'm going to make a column for my x-intercepts and a column for my zeros. Now zeros are what will turn this into 0. So I can see right here, the opposite of negative 2i is a positive 2i, and the opposite of 2i is negative 2i. So my zeros are plus or minus 2i, and that's it. Nothing else would give me 0. But since these are imaginary, are they also x-intercepts? And the answer is no. This graph would have no x-intercepts. If you're thinking, how does that work? Well, let's multiply this out and see it. And as you're working through this, we're going to see right now it's not too pretty looking. It's kind of an ugly looking equation with those eyes. But since these are opposites, which you're going to learn are conjugate pairs, we're going to see that the ugly goes away when you distribute. Watch what I mean. We're just going to distribute like normal. X times x is x squared. X times 2i is 2ix. Negative 2i times x is negative 2ix. And then negative 2i times a positive 2i is a negative 4i squared. The middle terms cancel out because one was positive, one was negative. And remember that the I squared is negative 1. Well, negative 4 times negative 1 is positive 4. So this polynomial in standard form is x squared plus 4, which if you think x squared plus 4 shifts it up 4, there are no x-intercepts. However, it still has zeros. Remember, since it's squared, it should have 2 zeros, and that 0 is 2i and negative 2i. That's how you do that example. Let's do one more, part B. Now we're going to do the same thing we did before. I'm going to switch it here. I'm going to make a column for my zeros, whatever will turn that into 0, and a column for my x-intercepts. What will turn this parenthesis into 0? What's the opposite? That would be 5. Here the opposite, what would turn it to 0 is this positive square root of 2i. And here that would be a negative square root of 2i. Since these are imaginary, they won't show up as x-intercepts. Only the 5 will. So this has one x-intercept, but it has 3 roots. 2 are just imaginary. Now, this wants to be written in standard form. So let's go over how to do that. Anytime that you have these opposites here, these conjugate pairs, multiply them first. It gets rid of the ugly, and then you can distribute it with the other one, okay? So I'm going to distribute just like what I did on the last one. X times x is x squared, and then I'm going to get square root of 2ix, and I'm going to get a negative square root of 2ix. And when I multiply these out, I'm going to get a negative. The square root of 2 times the square root of 2 is 2. why the roots are what they are. Like, if you were to solve this, I subtract 2 and I take the square root, and that gives me plus or minus square root of 2y. But we're not done yet. We don't have f of x in standard form. We still need to distribute it with what we have here. When I do, I'm going to get x cubed plus 2x minus 5x squared minus 10. And there's no like terms. It's not quite in standard form because it's not in order of exponents high to low. So I'm just going to change the order of the middle terms. So that's going to be minus 5x squared first, then plus 2x minus 10. So this is our polynomial in standard form. Those are the zeros, those are the x-intercepts. When we go on to part C down here, maybe take a second and try to think ahead. What are the zeros? What are the x-intercepts? How do we get that in standard form?